We're now going to take what we know about sequences and examine what it means for a sequence to have or not have a limit. We'll motivate the discussion by examining a bouncing ball so that its first bounce is 50 feet high and each subsequent bounce is 60% of the previous bounce. We can see the heights of these bounces modeled in the animation below. If we consider the sequence of bounces, b sub n, then we can ask ourselves, what happens to the height of the bounces as n gets larger and larger? We can write this sequence as the geometric sequence b sub n equals 50, the height of the original bounce, times 0.6 raised to the n minus 1 power. Then our question, what happens to the height of the bounces as n gets larger and larger, is equivalent to finding the limit as n goes to infinity of b sub n. Let's define some vocabulary. If the terms of a sequence approach a unique number, let's call it L, as n increases, then we say that the limit as n approaches infinity of a sub n is equal to L. That limit exists, and the sequence converges to L. On the other hand, if the terms of the sequence do not approach a single number as n increases, then the sequence has no limit and the sequence diverges. We know that as our ball bounces, the bounces are getting smaller and smaller and smaller. And so we can say that the limit as n approaches infinity of our sequence b sub n that represents our ball bounces is going to be the limit as n approaches infinity of 50 times 0.6 to the n minus 1, and that is equal to 0, and our sequence of bounce heights converges. On the other hand, we could consider a sequence such as one from compound interest, so we could imagine that we have the sequence of amounts in a bank account where we invest $1,000 at 5% interest, compounded annually, so we get the sequence 1,000 times 1 plus 0.05 raised to the n power. If we take the limit of that sequence, we know that the interest will continue to compound, and over time the amount of money we have in our account grows larger and larger, so this limit is infinity and this sequence diverges. It won't always be the case that we can use what we know about the real world to reason out the limit of a sequence. So now we're going to explore some techniques for finding limits. Our first technique will utilize all of the techniques we have for finding the limits of functions. So let's suppose that we have a sequence a sub n that is defined by a function f of n. F of n is necessarily a function whose domain is the integers. However, we can examine its counterpart, the function f of x, defined over the real numbers. And then we can examine what happens to the limit as x approaches infinity of f of x. We'll see that there are 3 distinct cases for examining the limit of a series when comparing it to the limit of a function. If the limit as x approaches infinity of the real valued function f of x is equal to L, then we can conclude that the limit of the sequence a sub n is also L. That would mean that the sequence converges. If instead the limit as x approaches infinity of f of x is either positive or negative infinity, then the sequence a sub n diverges and has no limit. In the last case, if the limit as x approaches infinity of f of x does not exist, then we can't conclude anything about the sequence itself, a sub n, and we need to try some additional techniques. Let's look at a few examples to understand each of these cases. So first, let's consider the function, or the sequence f of n equals a sub n equals 1 over 2 to the n. If we write out a few terms of that, we see that that's the sequence 1/2, 1/4, 1/8, and so on. Using our rule, we know that the limit as n approaches infinity of f of n is related to, and perhaps equal to, the limit as x approaches infinity of the function f of x, where that function is the function 1 over 2 to the x. But we know that as x goes to infinity, 2 to the x gets infinitely large, which means that we're dividing by a very large number and this limit is 0. Therefore, we can conclude that the limit of the sequence is in fact 0. Now let's consider the sequence a sub n is equal to 2 minus n squared over n plus 2. If we expand out some terms of that, we see that this is the sequence 2/3 when n is equal to 1, -1 when n is equal to 2, -7/5, -7/3, and so on. We can compare this limit as n approaches infinity of our sequence a sub n to the limit as x goes to infinity of the function 2 minus x squared over x plus 2. Now we know we have some limit techniques we can use here. In particular, we can divide by x on both the top and the bottom. Which gives us the limit as x approaches infinity of 2 over x minus x all over 1 plus 2 over x. Which becomes, we can see that as x goes to infinity, the 2 over x terms are going to go to 0, which leaves us with the limit as x approaches infinity of negative x over 1, which is going to be negative infinity. So that tells us, because this is negative infinity, that the sequence a sub n diverges. In order to illustrate our last case, we're going to look now at the sequence a sub n equals the cosine of 2 pi n. If we look at the function f of x equals the cosine of 2 pi x, we can see from our illustration that the limit as x approaches infinity of f of x does not exist. The function oscillates between -1 and 1, no matter how large n gets. This tells us that we actually don't know anything about the limit as n goes to infinity of a sub n. And again, looking at our illustration, we can see because 2 pi n means that for every integer n, we're making a 1 lap around our unit circle. The cosine of 2 pi is going to be 1. The cosine of 4 pi is also 1. The cosine of 6 pi is also 1. So this sequence is actually the infinite sequence consisting of nothing but ones, which means that the limit as n approaches infinity of a sub n is actually 1, and this sequence converges. So again, to reiterate, if the function limit doesn't exist, we still have to do a little bit more investigation to determine whether or not the sequence limit exists. Given that we can consider the relationship between the limit of a sequence and the limit of a corresponding function, that means that all of the tools that we have when calculating those limits are now available to us. We'll look at some other examples that put those tools to use. So, for instance, we're going to explore the sequence a sub n equals the natural log of n over n to the 1.2. And we want to look at, does this sequence converge or diverge? And if it converges, what value does it converge to? So we can instead look at the limit as x approaches infinity of the function f of x, which would be the natural log of x over x to the 1.2. And when we examine that limit, we can see that the top, the natural log of x, goes to infinity, and the bottom, x to the 1.2, also goes to infinity, which means we're in the infinity over infinity case for this limit, and we're allowed to apply L'Hopital's rule. So that means that the limit as x goes to infinity of our function is going to be the same as the limit of the derivative of the top, 1 over x, over the derivative of the bottom, 1.2x to the 0.2. Now we can do a little bit of algebraic simplification on that. This becomes the limit as x goes to infinity of 1 over 1.2 x to the 0.2 times x, which is, of course, using the rules of exponents, the limit as x goes to infinity of 1 over 1.2 x to the 1.2. Our denominator is getting infinitely large, which means that we now know that the limit as x approaches infinity of this function is equal to 0. And because the limit is 0, we then know that the limit as n goes to infinity of our sequence a sub n is also equal to 0, which means that it converges. We also have a version of the familiar Squeeze theorem for limits that applies to sequences. To use this theorem, if we have three sequences, a sub n, b sub n, and c sub n, so that a sub n is less than or equal to b sub n is less than or equal to c sub n for all integers n greater than some index n. In other words, b sub n doesn't have to be trapped between a sub n and c sub n for its entirety, but there has to be some number where after that number, b sub n is always stuck between a sub n and c sub n. Then we know that if the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of c sub n, and both of those are some number L, then the limit as n goes to infinity of b sub n must also be L. As an example of this, let's let b sub n be the sequence defined by 3n squared plus 2n plus 1 all times the sine of n divided by 4n cubed plus n. We know that negative 1 is less than or equal to the sine of n is less than or equal to 1 for all values of n, which means that if we let a sub n be the sequence negative 3n squared plus 2n plus 1 over 4n cubed plus n, and we let c sub n be the sequence positive 1 times 3n squared plus 2n plus 1 over 4n cubed plus n, then it will be the case that a sub n is less than or equal to b sub n is less than or equal to c sub n for all values of n. If we look at the limit as n approaches infinity of negative 3n squared plus 2n plus 1 over 4n cubed, we know that we can consider the equivalent real valued function. This is similar to the idea of a horizontal asymptote, which means that this limit, because the denominator has a higher degree than the numerator, this limit is exactly 0. Similarly, the limit as n approaches infinity of c sub n, 3n squared plus 2n plus 1 over 4n cubed. Same rule applies here. The power in the bottom is higher, so this limit is also 0. That means that 0 is less than or equal to the limit as n approaches infinity of b sub n, which is less than or equal to 0. So we can conclude that because the limits of a sub n and c sub n are equal, they must be the same as the limit of b sub n's, which is also going to be 0. We have a rule for evaluating limits when our sequence is geometric. In particular, if our sequence a sub n is of the form some constant a times r to the n, then the limit as n goes to infinity of that sequence is going to be 0 if the absolute value of r is less than 1. If r equals 1, then the entire sequence is just the sequence a, comma a, comma a, and so on and so forth. So the limit as n goes to infinity of that sequence would be a. In our last case, the limit as n goes to infinity of a sub n is not going to exist if either the absolute value of r is bigger than 1 or when r is equal to -1. In the latter case, the sequence would just bounce back and forth between positive and negative values of a and not converge on any one particular value. Our bouncing ball example is an example of a geometric sequence with our a value of 50 and an r value of 0.6. And we saw that the limit as n goes to infinity of the ball bounces was the same as the limit as n goes to infinity of that geometric sequence, 50 times 0.6 to the n minus 1. And since r here has an absolute value less than 1, that limit is in fact 0. Our next method for evaluating limits of sequences is going to be to look at some relatively common components of sequences and compare how they grow. And so we're going to use a method of comparing growth rates. So we're going to consider the set of components that are in this list that we see here. So we have functions of the form ln to the q power of n, where q is some integer. And then we have functions of the form n to the p, where p again is some integer greater than 1. We have functions of the form b to the n factorial, and then n raised to the n power. And all of these depend on p, q, and n being bigger than 1. A word about notation. The double less than signs you're seeing, comparing those sequences to each other, that's the mathematical notation for much less than instead of just less than. And so we'll see in this video that we can compare, using the graphs of the corresponding real valued functions, we can compare the growth rates of these functions and see that they do in fact satisfy that string of inequalities. So first up, we have the function ln of q to the n, and we can see right away that n to the p, the next function, is in fact bigger than it for almost all values of n. b to the n starts off smaller, but that we can see once n gets past about 20, it's bigger. N factorial grows really, really fast. And then, of course, at the end of the line, we have our n to the n function, which is the fastest growing of all of them. This is useful to us because if we have a sequence that involves ratios of sequences of this type, then we know something about their limits. So the rule is that if a sequence a sub n appears before b sub n in our list, then when we take the limit as n goes to infinity of the ratio of an over bn, we get 0 because the lower valued function is on the top. And if we flip that over and take the limit as n goes to infinity of b sub n over a sub n, we end up with infinity. To see this in action, let's consider the sequence 4 to the n plus 5n factorial all over n factorial plus 2 to the n. And we want to investigate what is the limit as n goes to infinity of this sequence. So we're looking at the limit of 4 to the n plus 5n factorial over n factorial plus 2 to the n. We can use a technique we've used before with rational expressions. We're going to divide everything through by n factorial. And so if we do that, we get 4 to the n over n factorial plus 5n factorial over n factorial. And then our denominator is n factorial over n factorial plus 2 to the n over n factorial. And then we can simplify. So we have 4 to the n over n factorial on our top left, but the top right just becomes 5. And then on the bottom, n factorial divided by n factorial is 1, and we have 2 to the n over n factorial. But our list tells us that 4 to the n is much smaller than n factorial, and 2 to the n is much smaller than n factorial, which means that as n goes to infinity, the limit as n goes to infinity of 4 to the n over n factorial must be 0, and the same thing for 2 to the n over n factorial. So we can see that within our limit here, we have this piece is going to 0, and that piece is also going to 0, and so we end up with 5 over 1, which is, of course, 5. So far, all of the limits that we found for our sequences depended on those sequences being determined by formulas. Right now, we're going to take a look at how we might think about limits for recurrence relations. And this idea is going to rest on a proposition that I think is fairly straightforward when one thinks about it. And that is the idea that if a sequence has a limit, if the limit as n goes to infinity of the sequence a sub n is equal to L, then the limit as n goes to infinity of the sequence a sub n minus 1 is also equal to L. Since we're considering what happens as n gets infinitely large, dropping the index on our sequence by 1 isn't going to change the ultimate limit. So we're going to use that in a context that I think is fairly useful. So we have this problem here that many people take aspirin on a regular basis to prevent heart disease. And so we have a person here who takes 80 milligrams of aspirin every day, every 24 hours. If that aspirin has a half-life of 24 hours, so that after every 24 hours has passed, whatever's in your drug, half of that has been eliminated. What we want to do is find a recurrence relation that establishes a sequence, d sub n, that tells us how much drug is in the blood after the nth dose. So in other words, on the nth day of taking the aspirin, given that our day 1 amount is 80. And then we're going to look at computing the sequence of such a limit. We're going to have to start off with the assumption that the sequence has a limit. And then what we're going to do is use our rule to find the steady state amount of aspirin that would be in the bloodstream from someone who takes aspirin every single day. So to start this off, let's come up with a definition for the sequence. So we're given that d sub 1 is equal to 80. And we also know that on any given day, day n, we have half as much in our bloodstream as we had the day before. So we can say that d sub n is half of d sub n minus 1. But then we also on that day add another 80 milligrams of aspirin. So this is a recurrence relation for this sequence. We're told to assume that this has a limit. So in other words, we know that the limit as n approaches infinity of d sub n has to equal some number. We'll call it L. But our rule tells us that that is going to also be the limit as n approaches infinity of d sub n minus 1. So let's replace d sub n on the left-hand side with what we just determined that it's equal to. That is going to be the limit as n approaches infinity of 1/2 d sub n minus 1 plus 80. And then we can use some limit rules, move the 1/2 out in front. And then, of course, the limit as n goes to infinity of 80 is just 80, so we have a plus 80 over here outside of our limit. But we know by our rule that this was L, and that was also the limit as n approaches infinity of d sub n minus 1. We can replace this expression right here. This right here is also L. So what's happened is we've got this equation now. Replacing our instances of the limit with the value of the limit, which is L, we get 1/2 of L plus 80 is equal to L. Now we just do algebra. That tells us that 80 must be subtracting 1/2 of L from both sides. 80 is 1/2 of L, which means that the limit is 160 milligrams. So we can assume that taking an aspirin every day, if this information about the half-life of aspirin is accurate, that over time the maximum amount that would build up in one's bloodstream would be 160 milligrams. In our wrap-up, we'll just take one last look at all of the things that we talked about here. First, we defined the limit of a sequence, as well as the words converge and diverge. We discussed how we could apply function limit rules to find the limits of sequences. We looked at the Squeeze Theorem as it applies to sequences. Then we found some rules for geometric sequences, in particular rules that rely on the absolute value of the ratio in our geometric sequence. We used function growth rates to look at the limits of ratios of sequences. And then lastly, we used a technique for finding the limits of recurrence relations and explored an application of that limit of a sequence.